Cool. Yeah. So, I just want to talk a little bit about something that I had a little bit of fun with last week. So it should be a little short and sweet and really relevant to Go developers in general. Just to start introducing myself, I'm currently a member of technical staff at Tailscale. If you haven't heard of Tailscale, it's the one that the place where Brad Fitzpatrick works. So he's pretty famous for doing Go. I stream software stuff on Twitch. I have 2 dogs, and you can follow me on GitHub or Twitter if you want to. Up to you. Another reminder, I do have a conference coming up. It is in October. It is the best Go conference in my opinion. I'm a huge GopherCon fan, but I do think this is the best conference. And it's all because of the people that attend. So we've had the best people attend this conference, hands down. Oh yeah, and I do build Star Wars Legos. Cool. So I don't know. I have always I guess this is something I've kind of always done. But cross compilation is something super common in Go, right? One of the nice things about Go is you can compile a binary that runs on a local operating system, but a lot of times we're developing on a different operating system than what we have in production. I know I develop in Mac and have always deployed to an Alpine or Ubuntu operating system. So to deploy that Go server, I have to compile a Linux binary instead of the Mac binary that I currently run on. So something super common, everybody ends up doing it Go. And like I said last week, I was at work. We were running into a problem with this where my M1 Mac was not compiling correctly for the Linux 84x60. I don't know exactly what we use. But we do have but for the basically the EC2 instances that were running in AWS do not compile from the M1 Mac I have. So it was, kind of fun and interesting for a minute. So generally speaking, when you are doing cross compilation, there's 3 main methods with Go. It is built into the Go build system. It can be done with Docker builds, which is my preferred way, and how I typically do it for all personal projects, and how I do anytime I deploy Kubernetes. And there also is using Zig Lang. If you haven't heard of Zig, it is a new, pretty relatively new language, but super common use case is for Go compilation, or just language cross compilation in general from all languages. I've seen it with Rust and with Go and with C++. So it's a lightweight language often used to replace C++ and things like compilers. With the Go compiler, it's pretty simple. If you need to compile to a language you're not running on, all you've got to do is pass the Goose and the GoArch environment variables. You can export them, or you can set them inline, and just run it on whatever you want. This would be for a Windows AMD 64. There's also Linux. And if any of you are adventure hobbyists, you can also just straight up support WASM builds using JS and WASM. Without any fancy compilation, any fancy tooling, and just deploy straight to WASM. I didn't realize that for a long time. I always thought that you had to use like a custom compiler and this custom packages and all, all TinyGo and all that special stuff that the community builds. But no, it's just right out of the standard library. You can compile the WASM and deploy cool front-end apps without really having to rely too much on other open source technologies. And yeah, then you can just take that binary, plug it on whatever VM or production server or Raspberry Pi you would ever want, and just have it run. The next one, again, my preferred, is just using Docker. That way the Docker runtime is dealing with the OS you're running on, and I technically always just build it in the Docker app. So this would build on Alpine. This is like the default Docker file I use for all of the Go apps. Whenever I generate a new repo, I use this. So that way I can build on my M1 Mac and just always build this image and deploy it wherever I want. And it's not a problem at all. Super common. And then last, again, is Zig. This again, when we were having issues at work, it was because the M1 Mac does not build for the Linux operating system that we have. We push our binaries from local machines. Still, we're pretty small and scrappy, but M1 Max does not build correctly for just straight out of the box Go operating system for Linux. It doesn't cross compile straight across, but Zig does do that for you. So you don't really have to include much. Just install Zig, use the Zig C target and the C compiler for Linux x86 with the Go build, and it works pretty seamlessly and it just, produces that same binary you would expect otherwise. And Zig's super lightweight, easy to use. And honestly, I did not see Zig taking any traction in like the community until people started using it with the M1 Mac for Linux builds. This is a super common solution for that. I have a link to an article that kind of explains through it and walks it through so that you can see after you've done an installation of Zig how it works. This is the solution we're approaching at work, is trying to do a Zig compiler. Again, mostly because it's super easy, and it builds the exact same Go binary that we were using before, just using a Zig-based compiler as opposed to a C++ compiler or a Go-based compiler. And yeah. It's been 7 minutes. Didn't I say 10 to 15? So I've got 3 more minutes.
You're good.
Basically, take away from this, you can develop on whatever machine you want comfortable. I'm a huge advocate of having customized dev environments. That's why I use Vim. That's why I maintain my own Vim. It's what works best for me. And you should always use what works best for you individually. And that includes whatever machine you want. And that shouldn't limit your ability to deploy things. And you can use whatever compiler you want to do it. Again, I love Docker. I deploy with Docker. That's my preferred tooling just because Docker is so ubiquitous right now. But if you're comfortable just deploying straight Go binaries and the Go compiler is not working, try Zig. And just a reminder to get your tickets for GoWest. I really hope to see you there. And thank you so much for listening to my talk.
Awesome, Miriah. Thank you so much. That was truly lightning and truly helpful. Anybody have any questions that they would like to ask Miriah tonight? Anybody? Going once? Going twice? Okay. Awesome, Miriah. We'll really appreciate you stopping by. Very excited about GoWest. Thanks again for everything you do for the Go community. It's really, really appreciated. And definitely looking forward to the event itself. I'm looking forward to logging on a bit and enjoying also. So thank you again. That being said, I'd like to introduce our next speaker tonight, and want to thank Nishant for coming out and sharing a little bit tonight. Nishant, I'm going to let you share your intro.
Perfect.
You do it amazing justice, but thank you for taking the time to join us here at GoSF this evening.
Of course, really excited to be here and meet everyone. Let me make sure my screen sharing is working.
Perfect. Your stage is yours.
I was just telling someone this yesterday. I can't believe we're 3 years into this virtual working situation and still haven't figured out a good solution for screen sharing. But let me know if this works, if you can see just the slides and not everything else on my screen. Good, perfect. All right, nice to meet you, everyone. I'll start out with the intro page. I'm here to talk about heap optimizations for Go systems. To start off, I'm an engineering manager at Pinterest. I work in the ad serving platform team. It's good to see Steve here today and hear his voice. We worked together for a couple of years, 3 years ago, pre-COVID, and haven't spoken since. So super excited to see you here, Steve. What my team does is we're responsible for the performance and reliability of our ad delivery infrastructure. Pinterest last year did a little over $2 billion in ad business. So any downtime at all is pretty much unacceptable. And every single improvement that we can make to our performance and optimize our systems better essentially results in a huge saving, whether that's on the latency front, whether that's on the infra cost front. And like they say, a dollar saved is a dollar made. So this was essentially about 6 months of my life. We were essentially taking 2 different Go services and merging them into one. And the biggest thing we ran into was tail latency concerns. And after a lot of head bashing, we realized that the main problem was the garbage collection. So here to talk a little bit about what went wrong and how we went about fixing it. So to start off, maybe a quick intro to memory management and how it works in Go. So memory management itself, at a high level, refers to the idea of allocating memory for a program upon request and releasing it for use once that memory is no longer needed by your program. The memory can then be used by other programs. So the great thing about Go is that it does not require users to perform any manual memory management. So users don't need to be manually allocating or clearing memory. Both these functionalities are taken care of by the runtime. The good part about this, it minimizes the chance of memory leaks. The negative side of this is it gives the user less flexibility in how much control they have over their application. How it actually works is the Go garbage collector runs every time that the heap hits a certain target size that is internally tracked. By default, this happens when the heap grows by 100% since the last garbage collection ran. This is configurable, so there's an environment variable you can set to make garbage collection either more aggressive or less aggressive based on your needs. Most users never need to worry about it, but in case that is something that does sound useful to you, it is possible to do that. And how the garbage collector in Go actually works is it uses what's called a tricolor algorithm for marking objects. So what that essentially means is every single object that is on the heap is divided into 3 sets based on color. So the first one is white. If it's in the white set, it means it's collectible, means that it's no longer in use in memory. If it's in the black set, it means it's not collectible, means it's definitely in use in memory. And the last one is gray, which means we're still in the process of determining whether it's collectible or not. Basically, by using this tricolor algorithm, Go is able to run its garbage collector concurrently with the main program without having a stop the world pause, which other languages in the past, for example, older versions of Java prior to ZGC being released, was a huge source of performance concerns. So the next question is, if the Go garbage collector is running concurrently with your main program, how does that actually impact your performance? So in order to actually run the garbage collector, Go does take some percentage of CPU resources. By default, it aims to utilize no more than 25% of your CPU resources. The goal being obviously to minimize the impact on program performance and your system's latency. However, when memory pressure is high and the garbage collector needs to run very frequently, or there is just a very large heap in question that it needs to scan, the garbage collector may start to steal resources from the main program going above this 25%, which obviously can severely hinder your application's performance. There is a silver lining to that though. By stealing more CPU resources, aka Go routines, to assist with the garbage collection, it's essentially reducing the rate of memory allocation as well. And this makes sure that the rate of memory allocation is not higher than the rate of memory cleanup, which means it prevents, or in theory, severely reduces the risk of out of memory errors. So what actually causes the garbage collector to run slower? When the garbage collector runs, the first thing it needs to do is scan every single object that is on the heap to see if it's still in use or not, which is what we discussed as part of the tricolor algorithm. So as the number of objects in the heap grows, so does the amount of time that the garbage collector needs to spend scanning the entire heap. So then the question is, what is actually on the heap? And at a high level, memory allocation falls into 2 different areas. There's the stack and the heap. A stack is all the memory that is required for a function itself. So any temporary variables that are only required for the scope of that function's lifetime go on that function stack. Once the function is done executing, that stack is cleared. And if those variables are not moved anywhere else, there's no way of accessing those variables later. So any variables that need to live beyond the scope of a certain function are assigned to the heap. And the way Go determines this is through something called escape analysis, which I'm not going to dive into. But high level, the idea is if the object is only referenced within the scope of a particular function call, it's going to live in the stack. If not, it'll be moved to the heap. So hopefully that gives you an idea of what the garbage collector is doing from a 30,000 foot view and what may cause it to run slower than before. So the next in retrospect, intuition is the first thing that can help guide you in the right direction. So first off, if you're seeing high tail latency, and the way we typically talk about latency is in percentiles. So in this case, what I mean by high tail latency is if you're seeing like high P90 or P99 latency. So if your requests are running much slower than average, that could be a symptom of garbage of the GC causing increased CPU load on your system. Essentially because this garbage collector only runs periodically. So if you're seeing this latency spike occasionally, there's a good chance that the garbage collector could be causing it. So if you see high tail latency, think about GC. And the next step is, how do you confirm that hypothesis? There's a few ways to do that. The one that I found the most helpful is there's this Go runtime variable called go debug equals GC trace equals 1. If you run your binary with this variable set, so you would essentially just set this in your CLI command as you're running your binary. It'll force your program to output debug logs for every single GC cycle as it runs. So every time the garbage collector is triggered, it'll output some logs that show you how much time is spent in the various GC phases, how many resources the garbage collector has consumed over the lifetime of your program, what the heap size is, so on and so forth. And I'll just show you an example on the next page of what that looks like. But the summary here is, since this is going to be printed out every single time GC starts, what you can do is add a background thread essentially to print out your system's latency, or at least add a timestamp to this Go GC log. And then you can see if your increased latency aligns with the start and end times of GC, which gives you a pretty good idea that the garbage collector is likely what's causing your system to run slower than before. So here's an example of what a GC trace output looks like. And credits to Arden Labs for this image and the detailed breakdown of every step. If you want to take a look at this blog post in more detail, you can just Google GC trace Arden Labs, ARDEN, and that'll give you a good idea. He goes into a lot of detail about every single thing. So you can see we have how many times GC's run since our program started, how much time has been spent on GC, what percentage of total CPU usage available can be attributed to GC, so on and so forth, how much wall clock time, how much CPU time was spent in GC, so on and so forth. And you can actually see the heap size before and after GC as well to get an idea of how much work does the garbage collector need to do per cycle. Like we said, typically the larger the heap means the more work. So once we get this, like I said before, we can essentially let this GC trace run, add a background thread to print out our system metrics and look for a correlation. So once we have this, we can get to a fairly decent conclusion about whether the garbage collector is our problem or not. Let's say we get to the conclusion that it is. The next step is to take a look at our heap itself and profile our heap usage. The great news is that Go comes with some good built-in tools to study our heap usage. I'm going to talk about two in particular here that I found really helpful. The first one is the memstats package, and the second one is the pprof package. This lets you see, the memstats package lets you see statistics about memory allocation by your program. And pprof allows you to run system profiles and get a UI and a much more detailed view into the actual heap usage. pprof also lets you see CPU usage and blocking Go routines, mutex locks, etc. So it's a really powerful package. I'm going to focus purely on the heap profiles for today. But let's start with memstats. It exposes, I think, 20 to 30 different stats that might be useful. There's a link I can share these slides, or if you want to send them out later as well. The Go docs have a detailed breakdown of all the stats available in the memstats library, but these are the three that I use very often. The first one is heap object, shows you the number of heap objects that are currently allocated. Next one is heap alloc, shows you the number of bytes that are allocated to the heap. And then the last one is heap sys, which is how many bytes have been requested from the OS for your program. So the first one here is what I typically look at the most, is how many objects are on the heap, because as you make things that you think are improvements, to test it out, you can essentially keep your program running and look at the heap objects before and after your change. And if the number of heap objects is dropping, that's a good indication that your garbage collector's performance is likely going to improve. So here's a quick example program. Feel free to copy this and run it on your own. But essentially, we're just allocating an array over and over, forcing heavy allocations, forcing a GC cycle, and printing out the memstats to see how the system looks at various stages. So here's a sample output. As you can see, the number of heap objects is continuously increasing. And after we run a GC cycle, the number of heap objects drops, which is the last one. And sorry, this is something you can do even in your main production systems. The numbers will obviously be vastly different and the behavior may not quite be as predictable, but this can help give you a good idea of what your system looks like at various cycles. And you can tell exactly how often and exactly where GC is running because the heap objects and heap alloc is likely to drop. So the next thing to look at is pprof. Pprof has this very easy to use CLI that you can run commands with to generate these profiles. So the first step to do is expose, sorry, I think I'm missing one slide here, but essentially in your application startup code, you just need to make sure to add one API endpoint that points to an HTTP API endpoint that points to the inbuilt pprof profiler. I can share that line after I'm done with the talk for anyone who's interested. But once you have that line in place, once you have that endpoint exposed, you can run this command line, well, this command, go to pprof, point it to that specific port, and get a heap profile for your system. And there's a few options to see exactly what you're most interested in. Like we said, we're typically interested in in-use objects, so you would look at that one right there, the second option. And this will essentially download a .pb.gz file to your local computer, put you in an interactive command line to start visualizing that data. And there's a bunch of cool commands you can run to see exactly what can happen. The easiest thing to do is just run help and it'll show you all your available options. What I like to do is typically run this command, get the file locally downloaded, and then run a second command that I'll share in a second in a new terminal, which essentially will open up your profile data in an interactive web browser. So the command for that is you just cut out the tool part of here. You just say go pprof, and then you point to your path. Sorry, it is go tool pprof, and then you need to add what port you want to run on locally, basically. So the bottom command here, where the port is in blue, you just pick any random port that you know is not in use by any other application on your local machine, and it'll pull up a web page showing you a much more interactive UI that shows you visualizations like this. So this is just a sample I pulled off the internet, but you can basically see the number of objects in use by various call stacks. And this can really help. This can be really helpful in identifying which parts of your code base might be hotspots. So in this case, we can see 45% of our in-use objects are coming from this buffio.newReaderSize method. So this might be an indication that we're creating too many readers. So one thing we could do here as an optimization is either create an object pool so we're not constantly creating these readers, or potentially create a single reader and just reuse it over and over. This could be an indication that we're creating this reader in a for loop, for instance, which we probably don't need to do, so on and so forth. Again, it might be unavoidable, but this gives you an idea of where to focus your efforts. The second visualization that I find really helpful is this flame graph. It's similarly very interactive. You can click on any bar, any call stack in here, and it'll zoom in and show you a drill down. The width of the call stack here is based on the number of heap objects allocated by that call stack. So this gives you an easy idea of where to focus. Just focus on the wider call stacks, and that's a good way to go. So this will essentially help you identify which methods in your code are the hotspots and that you need to focus on. Then you can go back to your original interactive CLI that it put you in after you ran the initial go tool pprof command. And there's this really helpful method just called list. So you type in list and the method name that you want to learn more about. And it's going to print out line by line exactly how many objects are allocated by that line in your terminal. So in here, hypothetically based on the last flame graph, I saw that this create catalog map method was allocating a large number of objects. Over here, it looks like 80% of total objects were allocated by this method alone. What I can do is then run this command and see exactly which lines in this method create how many objects. So what's interesting here is that lines 237 and 241 are both allocating the same number of objects. That sounds a little funky, and might give us an indication of where to focus our efforts. So we'll come back to that in a second. But let's talk about at a high level what you can do to impact the limit of your garbage collection. So again, to reiterate, garbage collection becomes more expensive when we have a large number of objects on heap, or when the rate of your memory allocation is really high. So if we can lower the number of objects on heap, or if we can reduce the rate of object allocation, we can typically see improved performance from our garbage collector. The third thing we can do that is really interesting that I did not know about at all prior to this project was that you can actually optimize your heap, your memory usage by just changing your data structures a little bit. And this in turn can also obviously mitigate the impact of garbage collectors. So let's go through them one by one. The first one, like you said, is reducing these long living objects. So one quick way to do that is creating those objects on demand instead of having them continuously living on your heap. So for instance, let's say we're some sort of online service that is handling a user request. And for every single user request, we need some sort of user features. Maybe they're just count features. I work in Pinterest ads. Hypothetically, this could be the number of times the users clicked on an ad from a particular advertiser in the past. So one way to do this is we essentially keep all of that data in a large map keyed by user ID to these count features in memory all the time. The alternative way to do this is we compute this on a per request basis only for the user in that request. Or perhaps we fetch it from an external source only for that user in that request. Obviously, there are some trade-offs here. Computing can be expensive. Fetching it from sending an RPC call to fetch it may be expensive. So those are trade-offs you need to consider. However, what this will do is reduce the number of objects on your heap, which will in turn improve your garbage collector's runtime. The second thing is you need to really be mindful of where you're using pointers in Go. So if you have a reference to a particular object, let's say again, going back to this user features object that we talked about, in there, if that object contains pointers nested within it, each one of those pointers will be considered an individual object in the heap because it's possible that that reference was passed somewhere else and that reference needs to live beyond the scope of the original parent object. So this can really quickly add up and result in a large number of objects on heap, which may not actually be needed to be stored in separate locations on heap. So where possible, if you can change these nested values to be non-pointers and just actual values, we can reduce the number of objects that the garbage collector needs to scan during the marking phase. And one thing to look out for here is that strings and byte arrays are treated as pointers, even if you don't directly declare them as such. So if you can potentially reduce the number of strings you're using, one example that we had in our system was we were storing a lot of dates as strings. Instead, if we used the time.time objects, those were now no longer considered individual pointers, and that actually led to a huge improvement as well. So here's one example, which really highlights the impact of removing strings. This is the same code stuff from before. Once again, calling your attention to the fact that lines 237 and 241 are both allocating almost 21 million objects, which is a little crazy. On line 237, we're essentially creating this catalog listing key, or line 240, we're creating this catalog listing key by passing in the product ID and seller ID. And then we're creating this map and using that string as a key within it. So in this case, what is actually causing these extra object allocations is the fact that the key is a string. So one change we can make here is instead change the key to be a simple struct instead, where we just create this like random struct that has a product ID and seller ID as two of its attributes, and use that as the key instead. And we can see that we reduce the number of objects in our heap by, I think 26 million was the saving here, which translates by 20%, which may not necessarily correlate with a 20% drop in latency or garbage collector time, but it does definitely make your garbage collectors work more lightweight. So the second thing we talked about is reducing the rate of object allocation. What this essentially means is if hypothetically for each request, you're creating a large number of these objects in bursts, and these objects only live for the duration of that request, it may be beneficial to use object pooling so that these objects can live beyond the lifecycle of just one request. The reason this is helpful is the heap does not look at objects that are in an object pool. And so it doesn't need to scan those continuously. It trusts you to manually clear those out. So that is the most flexibility that Go gives you, are these object pools within the sync package. The catch here is that object pooling can often be tricky. So I usually recommend that people don't use it because it can very easily lead to memory or data leaks. So if you're not mindful of your object pool size, it could very quickly increase, use up a lot of memory, lead to out of memory crashes. The second thing to be really mindful of is if you're not properly sanitizing your objects prior to returning them to the pool. So once again, going back to a user features object that I've been referencing, let's say we have some identifiable information per user. Maybe we have their IP address stored in this user features object, and we're logging this user features object to some table later on. If we don't clear out that object properly, that object is going to be reused for a future request, and we may be logging one person's IP address to another person's log entry, for instance. So those are things to be mindful of, which is why I typically don't recommend it. But if you do find that this is something that your program is suffering from, essentially the start of every request, there's a huge burst in object creation, which will likely trigger a GC cycle right there, because like we said, GC gets triggered every time your heap doubles in size. If you're allocating a large number of objects, all of a sudden the heap is probably going to increase in size very drastically, causing GC to run immediately. This one is something I found really interesting. This is the next thing. Cleaning up unused data fields can have a huge impact. Since basic types in Go will always have default values. So if you have a Boolean field, it's going to default to false. If you have an int, it's going to default to 0, so on and so forth. And even though you're not using these fields in your application, an unused field still needs to consume memory to actually store this default value. The good news is, since it's unused, removing such a field is a no-op for your program. Making sure that something is unused can be pretty tricky, especially if you have a use case where you're logging these objects offline. That is something that can get a little hairy, but if you have a good IDE, it's at least very easy to see if these objects or these fields are being referenced anywhere in the code. And if not, you can pretty easily remove them. And by removing these fields, you're lowering your program's memory usage once again. The other benefit is you're making your code more readable and easy to understand. This one in particular is something that I had no idea about and I found really fascinating. So the Go memory allocator does not optimize for data structure alignment. More recently, I've heard that folks who come from a C or C++ background are very familiar with this idea. But in order to respect word alignment, the Go allocator will essentially add a bunch of padding in memory to make sure that all the fields of the struct are properly word aligned. So in this case, our first field is a bool. It allocates 1 byte. The second field is an int64, which needs 8 bytes. However, it can't directly add that right after the bool, so it needs to pad 7 empty bytes here in order to keep in with that word alignment. So all we did here was rearrange our fields. If you look at the bad object and good object here, they're the exact same fields. We just rearranged them, and we went from per object 40 bytes to 24 bytes, which is a 40% improvement here. And on our last slide, going from 64 to 40 bytes, if we add all that together, that's a 62% improvement just by deleting data that we don't need or deleting fields that we don't need and rearranging our fields in place. So if you think about it in a large scale system, which has 1,000 or 1,000,000 objects in use, a 62% improvement in memory usage can really lead to immense performance improvements. And additionally, if your system is actually something that's memory bound, you may be able to save a lot of money in your infrastructure costs by lowering your memory usage. So that's the last thing I had to share. To summarize, the Go garbage collector is awesome. It's really powerful, but it is not perfect. Most developers will never need to worry about how it works and its performance, since it's likely not going to impact you. But for systems that are pretty heavy, the garbage collector could lead to pretty significant impact to your program's performance. So understanding how GC works, how memory management works, and what tools Go has built in can really be helpful to understanding the problem and optimizing your system. And depending on your use case, you may actually see pretty significant performance improvements as a result of this change. Thank you for listening. If you have any questions, happy to take them now, or also happy to take them offline. Feel free to email me anytime, nroy@pinterest.com. I'll respond usually within a day.